All right, so continuing with this here, we just need to go ahead and do one more conversion step, and that is the centimeter to inches. Be careful here that you're putting the numbers in the right location. That 2.54 is associated with the centimeter. So that goes on the bottom, and the 1 inch goes on top. All right, so, oops. I'm not going to do it that way. So to save yourself a little bit of time on your calculator, you could actually do this calculation in your head, because that's just 10 to the 5, right? We have 10 to the 3, yep, it's 10 to the 5, so that could save you some time. So times 10 to the 5, and then lastly divided by 2.54, 4, and then we get a large number there. I'm getting 413,000, etc. So we'll go ahead and scientific notation to 3 sig figs, 4.13 times 10 to the 5, it looks like. Yep, 10 to the 5. And my units are inches. And that makes physical sense to me because the kilometer is pretty far. You know, it's just like what? Here, let's go back. All right, back to desktop, this one. And we were here. All right, so here's just another example. You have a stepwise conversion here that you could do. So for example, I would provide those conversions for you because those are all English conversions, they're not base 10. And the main thing here is that you're going sequentially to get from what you're given, and then the tool, the path that you have to get there, putting all that together such that everything cancels out properly and you have the proper units at the end. Be very careful of your sig figs, because remember, everything in the middle there is an exact number, right? So don't let those limit your sig figs. And then as we're going to see later this semester, we're going to have like these mole terms in there. Those are also exact numbers as well, because there's kind of like you're counting discrete objects there. You're counting moles. All right. I do want to work through this example here. So here we have the issue of units raised to a power. So when you have a unit raised to a power, you have to raise the conversion units to the power also. So don't forget you have to do that. And I believe we're going to have to do that here in this conversion. Looks like it, probably on the bottom one, I'm thinking. So that's the one I want to go ahead and work through. There we go. All right, so what was that again? Let me get back up. All right, so once again here, this was 8.57 pounds per feet cubed. And the question was asking us to convert this to gram per ml. So we basically have to figure out some way to get them to match, and we were given a conversion factor for the pounds to grams. So we got that part taken care of. So I think that'd be a good place to start. So the first thing I would do would be to go from pounds. Let's go ahead and keep the feet cubed in the bottom there. So the first conversion is going to go from pounds to grams, like that. We need some kind of bridge point to go between the feet cubed and the milliliter. I'm thinking we'll probably get to centimeter, and you'll see why here in a moment, why I want to go to centimeter. But before that, we should probably go to inches first. So I'm going to go from feet cubed to grams per inches cubed. And then from there, I'm going to go to centimeter cubed. And then lastly, grams per ml. Right, so let's go ahead and set this up. So 8.57. And the units here are pound per feet cubed. The conversion factor that we were given, I believe it's 4 point something, 450 something. Yep. So notice there I put the pounds in the bottom, and I believe it is 453.59 grams per 1 pound. And then the next step here, I want to go from feet cubed to inches cubed. So where do I put the foot term? Where do I put the inch? Yep. Since the foot is on the bottom here, we want the desired unit inches to be on the bottom, right? So it's the opposite of what this was. So we want inches on the bottom, foot on top, and that way the feet cancel, and then we're left with inches here. That relationship, if you don't remember, is 1 foot is 12 inches. A little side note here, I believe that the foot length was based off of one of the King Henrys, like the length of his foot. And then come to find out when they looked at his corpse in the tomb or whatever, his foot was about 10 inches. So he was overcompensating. I think that's pretty funny, the fact that he actually had a 10-inch foot, not a 12-inch foot. All right, here I need to make sure I cube it. So notice how I didn't cube this term at first. I didn't have to, because I did not need to do that to get the units to cancel. But I did here. So we had feet cubed need to cancel. We need inches cubed. All right. So the next thing we need to do, I believe we're going to have to cube one more time as well. I had that conversion earlier, and that was 1 inch is 2.54 centimeter. We need to cube that. And that way the inches cubed cancel out properly, leaving us with centimeter cubed. All right, and you guys remember the relationship between a centimeter cubed and a milliliter? 1 to 1. Yep, they are 1 to 1. They are equivalent. So I'm actually going to stop the calculation right here. I'm not even going to bother writing it out. So because I know that centimeter cubed is milliliter. So I'm just going to report my answer now as grams per ml. All right, so breaking out the trusty calculator. We have 8.57 multiplied by 453.59. And then go ahead and enter on that, divide. Don't forget, we need to cube this term, the 12 divided by cube to the 3rd power. And then lastly, we're going to divide by 2.54, once again, to the 3rd power. And I am getting 0.137. How many sig figs should my answer have? 3. So in general, when you're working on these conversion problems, the number you came in with is going to limit you. That's basically how much you're going to have. But one exception to that is doing temperature conversions. Then you have to worry about addition rules there. But in all these ones, they're all multiplication rules. So, all right, so final answer to 3 sig figs was 0.137 grams per ml. If you guys want to do a multi-step conversion for fun, I think it's interesting to calculate how many seconds are in a semester. There's a lot of seconds in a semester, but you can do that if you want. I'm not going to do it here. All right, and that's pretty much it for Chapter 1. So make sure that you guys do practice your temperature conversions, all that jazz. Make sure you're comfortable with it. I do have worksheets on Canvas to practice, and you also have stuff in the book, and then you have the stuff on mastering. So what I recommend that you guys do is that you work in the order of you do problems on paper first that aren't worth points, you then go to the online homework, do it there. That is points, right? You should always practice on paper first before you start putting yourself at risk of losing points. All right, we are not done for the day yet. I did want to go ahead and start into a little bit of chapter 2. We're probably going to go early today. Don't worry about it. You guys are all chopping a bit to get out of here. All right, so switch back. All right, so this is the chapter 2 discussion. This PowerPoint file is online. All right. So Dalton's atomic theory was figured out quite a long time ago. The 803 to 807. I do want to mention here that I think I mentioned it last time where the word atom comes from the Greek word atomos, which means indivisible. So here we have an element are made up of tiny particles called atoms. And then anytime you have any atom anywhere where you find it in space or on Earth, any atom is their equivalent no matter where you found it from. So what I mean by that is the hydrogen that you have in water is the same kind of hydrogen that's in butane fuel. I mean, yeah, those are two completely different molecules, but atomic-wise, they're the same. So hydrogen is hydrogen no matter where it's from. That's basically what number 2 is saying. And atoms of different elements have different properties as well. And we know that you guys probably remember from 103, the number of valence electrons does have an effect on reactivity as well as atomic size. So the point of that is that no two atoms are exactly the same. And then number 3, atoms cannot be changed into other types of atoms by a chemical reaction. In order for an atom to change its identity, that means the proton count has to change, right? And that falls into the category of a nuclear reaction, stuff that we're not doing. I don't recommend having students who are in their first semester of chemistry doing nuclear reactions in the lab. It's probably not a good idea. All right, number 4, compounds form atoms of one or more element combined, and a compound always has the same number and kind of atoms. That was that law of constant composition that we talked about last time, basically saying that all the different atoms of H2O are all going to have that composition. And then we have the word compound itself. I will use the words compound and molecule interchangeably. But just remember that they mean the same thing. All right, a few laws you have to know about. So first things first, we have the law of conservation of mass. This basically says that matter cannot be created or destroyed. One place where people might think that you may be proving this to be false would be to say where if you burn a piece of wood, that you have ash behind, and if you weighed the wood beforehand and weighed it afterward, obviously the ash is going to be lighter. But then where did the mass go? Was it destroyed? So where did the mass go? Kind of flies away. It's mostly the smoke, right? Smoke is a mixture of gas and solid particulates. So if you were to actually capture all the smoke that came off and got the mass of that, they would be equivalent. The confusing part of that is that gases do have mass, but they're less buoyant than air, so getting their mass is not as straightforward as putting something on a scale. But the thing is that matter was not destroyed when you burn something, it's still there. The interesting thing about this law of conservation of mass is you guys may have heard of Einstein's equation, E equal to mc squared. That's actually referring to mass loss during nuclear reactions, because the amount of mass that's actually destroyed correlates to how much energy is generated. You guys will cover that next semester, but it turns out that if you actually do destroy mass in a nuclear reaction, they release a ton of energy, because nature does not like doing stuff like that. There's a ton of energy in that nucleus. But for this class, go ahead and say that, okay, mass is conserved. The main way we're going to compensate for this or use this law, it's arguably balancing reaction with stoichiometry. You guys remember that stuff? That's basically a application of the conservation of mass. The next one we have here is the law of multiple proportions, basically saying that atoms of two or more elements may combine in more than one way. So in this example here, we have H2O, and then we have H2O2. And you have that joke, oh, Joe walked to a bar and said, I'll have H2O. And then his friend said, oh, I'll have H2O2. And then he died. Again, drinking H2O2 is toxic, but the thing here is we get extra, we can have different ways they can combine and make different compounds. And they have different mass ratios. You guys know what the name of H2O2 is? It's peroxide, right? And we're going to see coming up in this chapter, we're going to be doing a little bit of naming. And in general, in chemistry, if you have the per prefix, that basically means that you have extra oxygens. In a lot of cases, that's how it's used. So when you say hydrogen peroxide, it's basically saying you have extra oxygen. And then later on, we'll be doing things like perchlorates, that kind of thing. They have extra oxygens. And then later on in organic chemistry, we talk about peroxy acids. Those have extra oxygens in them. Or, sorry, peroxy carboxylic acids. Those have extra oxygens in them. All right, these experiments are basically ways that we figured out a bunch of these different principles here. The first one here is the cathode ray experiment. Basically, I don't want you guys to understand the details on how the experiment worked. I want you to be familiar with the experiment name and what they figured out. Does that make sense? So I'm not too focused on the details of the experiment because it's actually pretty complex, some of them, and all the little details they went through to figure this stuff out, but I want you to know the result. So the cathode ray and electrons experiment was a way that they were to use deflection to figure out the mass to charge ratio. So they did not get either one of those, they got a ratio of the two. It's the mass and charge ratio, which later experiments were able to tease out those different things separately. Interesting thing about this here is, does anyone know what kind of technology this led to that was used very heavily worldwide? They were commonly called cathode ray tubes, or a CRT television. You guys ever heard of that before? Yeah, that's actually what CRT stands for, is cathode ray tube. And they were actually this kind of technology. So if you happen to have one of those TVs laying around still, a real fun thing you can do is take a magnet to it while it's running. And it'll actually pull the particles left and right because they're all charged particles hitting it. And they're affected by a magnet. I remember I stuck one to the side of my TV as a kid, and I left it there, and we came home, and it was permanent. Our image was fully distorted to the right where the magnet was stuck at. I got in trouble, obviously. But it was funny because my dad got in trouble because for my mom because he showed me that I did that. All right. I am not too concerned about you knowing who figured it out per se, unless it's part of the name of the experiment. But this was Thompson. He did figure out the charge to mass ratio. All right. The next one here is the Millikan oil drop experiment. Sorry. Back up a little bit here. Basically, what he was able to do was figure out the charge and mass of an electron. So basically, if he was able to figure out one or the other here, which is basically figure out the charge, he was able to use work that previously that Thompson did to figure out what the mass was, right? Because it's just a charge to mass ratio. So basically, he was able to tease out both of these different things. This experiment looks like it was a pain in the ass to do. Basically, what this guy had to do was watch for hours as drops came through and count them as they came in one at a time. He did it for hours at a time. People have replicated this experiment in the recent years, and there are videos actually on their YouTube of people replicating this experiment. Very, very tedious. Don't want to really go on. This is actually related to the cathode ray tube experiment. Going over the 3 types of radiation here. Basically, I remember the gold foil experiment from last semester we talked about. That's basically what this is leading up to. Third picture. I'm just getting ahead of myself here. We'll backtrack here later, different types of radiations here, but it's not that too relevant right now. The main thing for electrical charge is that there are two charges, positive and negative. And then we have these electrostatic laws, basically stating that there are like charges repel, opposite charges attract. And does anybody know what kind of force that is, if you're thinking about it from a physics point of view, which force that's called? It's the Coulomb force. The letter C that they use for the charge in the charge for an electron is the Coulomb, and Coulomb was involved in a lot of this stuff. So yeah, they call it the Coulomb force, if you're thinking about it in terms of the different forces that you talk about in physics. All right, so here we have the so-called plum pudding model. This was one of the earliest models used for the atom back before the gold foil experiment was conducted. People thought that this was how the atom was put together. We now know that's not the case. So what happened is Rutherford set up a black box source of alpha particles. And if we were to go back, basically an alpha particle is a helium nucleus with a helium atom that's missing the electron. So it's basically a helium nucleus. So it's He2+. That goes out, and then what happened is if it were the plum pudding model, most of the particles would have just passed straight through, and then a small fraction of them would have been deflected. In this one, he did see that a lot of it did pass through, but more than expected were deflected here. And what that basically told him was that their atoms, the positive charges were concentrated into a small nugget, basically, and that's our nucleus. So the moral of the story here is that the scattering pattern led to the currently accepted model of the atom, which is the dense core for the nucleus. So here we have the dense core of the nucleus. That's where most of the mass for the atom is kept. And then we have the electrons in a big cloud on the outside. Does anybody know which subatomic particle is responsible for chemistry? The electrons, right? Yep, all the electrons, they're the ones that are governing chemistry. Basically, there are attractive and repulsive forces from the nucleus, but all like the workhorse of chemistry is all the electrons. And then actually one of the biggest parts of organic chemistry and why it's different than general chemistry is we're going to go over how the electrons do their work as a big part of that class. I'd say probably about almost all OChem 2 is tracing electrons and how they're moving around. And yep, they are the workhorse. All right, moving along here, as I just mentioned, the bulk of the mass of the atom is in the dense core. And then your electrons take up the space on the outside, but honestly, it's mostly just empty space. When we're looking at the size of an atom, we are typically talking on the angstrom level. Do you guys remember how small that was? Like how many meters, or how many angstroms are there in a meter? It was 10 to the 10, right? Okay, these are the charges that are involved and the different masses. I will definitely revisit this table in some calculations. We'll probably get it to it next week. In general, though, when working with talking about atoms, we generally give them a +1, -1, or 0 charge. But keep in mind that when I'm saying a +1, -1, or even +2, -2, it's that value times the Coulomb value. If you're going to be technical about it. And I believe the units on that were joules, if I remember right. All right. So I think I'm going to go ahead and stop here. We will pick up here with more practice problems and isotopes next time. Do you guys have any questions about anything we covered today? Or anything in general? You guys are all just pros of this stuff, right? Too easy? You stoic geometry now? Is that what you want? All right. We are going to. So you guys do have the Monday holiday, so use this holiday to study. Don't just hang out and watch TV all day or something. Yeah. I don't structure it the same way, but the questions are similar. So I typically do a mixture. I'll probably do 20 multiple choice and 2 complete with a short answer. Yeah. The one online they might be different, but the content is the same. What? I'm using XSplit now. This one actually came, I got a subscription with my camera, and they're like $200 a year. So I figured it was good because is it OBS? I'll check it out. This is really. I have 16 gigs of RAM here, so it should be fine. But it still bogs down my machine. I'm like, what? Yeah, you can show this difference. I'll check it out. Thank you.